I'm Rafah. I work for Microsoft Research, and I'm going to tell you about a technology we're working on that brings a lot of value for personalization scenarios, such as the one that Kara and Phil talked about. So let's talk a little bit about interactive learning for personalization. So let's take a content scenario. So we have Paul. Paul likes to browse news before he makes his weekly fantasy picks. We've got Susan. On the other hand, she likes to browse business news right before she calls her clients. And the question is, why should these two people with very different interests see the same content, right? So we should be able to personalize for each. And the second question, which comes up very often, is, okay, if you're personalizing content that changes constantly underneath your feed, how do you manage that? So a good personalization service is one that is continuously adapting to both content and context changes. Okay, so how do people do this in machine learning land? The most obvious way that is very, very common in folks that do machine learning for personalization is to use a supervised learning paradigm. So for those of you that are not too familiar, in a supervised learning paradigm, you get some training example. You spend X many millions of dollars labeling those things. You shove them into some supervised learner. There are multiple variety of these. And out comes a classifier, which in real time, you can give it a number if you've trained it on numbers. And for a certain amount of accuracy, it will give you that number. That works really well. Supervised learning is really cool. It's what made speech reco, Siri, Alexa, Google Home, all of these things came about from supervised learning. ImageNet, Image Reco, Face APIs, all of these are the results of a good machine learning, supervised learning algorithm. Okay, very good. How about news? What if you wanted to personalize any type of content, such as news, video feeds, playlist, and you're trying to maximize a business outcome? So suppose for the case of this scenario, you're interested about click-through rates. Okay, great. So let's build a supervised learner. You collect some user article click information. You build a feature set, and you learn how to predict a click given a user and an article. And in most companies, you deploy this in an A/B test. Everybody familiar with A/B testing? Yes. And it fails. And the question is, why is my A/B test failing? So what goes wrong? The first thing is Canada interesting to Rafah? Well, if you've never offered me Canadian news on my favorite website, so you have no historical data on me ever clicking on a news article pertaining to Canada, then your supervised learner has never seen that example. So if you're training on historical data, the answer is no. But it turns out I'm Canadian and I follow Canadian news. So you have to have the right signal to get the right answer. It's very important, especially when you're training over historical data. Okay, another thing that goes wrong is when you're creating supervised learning models that are based on historical data. This is real data, by the way, from a partner of ours. A model that's trained day one loses half its value by day two, especially when content is constantly changing underneath your feed. Because again, you're training on historical data, and unless you're continuously relabeling and retraining, those models over time lose their value. So here's another solution for you folks to consider. This is a new paradigm in machine learning called reinforcement learning. And here we use real end user feedback to train our models. So how does that work? So let's take our news example again. So we have a user, they come to their favorite news website. There's an online learner on the background. Whenever a user comes in, a user has context. So that means they have some feature set, the geolocation they are in, what type of device they're using. We call this the context X. Then inside that red box, there is a policy, a model that's choosing the best list of news stories for this user based on that context X. We call this an action. Now the key in reinforcement learning is that we don't stop there. The learner proposes an action and waits for the user feedback. That's why it's called reinforcement learning, because every time the user clicks, that's a positive reinforcement feedback for the online learner. It's exactly like teaching a puppy a trick. Every time the puppy does something, you give him a treat. That's a positive feedback. Every time the puppy does something wrong, you say, bad puppy. It doesn't learn from that. It's exactly the same principle. So that's kind of the paradigm that we use for personalization. Now, the key in reinforcement learning is a concept called exploration. So for the gentleman that asked about the cats and dogs, and reinforcement, at least in the type of reinforcement learning we do, suppose that you love space. So, and at some 80% of the time, we're going to choose for you space articles because that's what we learned that you like. But at some random 0.2%, 0.1%, 2%, we're going to choose a different article. So we'll show you cats, and at some configurable number, we say, you know what, we're going to explore the space and see if this gentleman actually likes a little bit of dogs. So we'll show the dog, and then we'll observe your reaction to the dog. And if you give us a positive feedback, we say, oh, well, okay, maybe it's not just cats. Maybe he does like dogs a little bit. And so this exploration is very, very powerful. And this is not complete random exploration. So it's exploration over the set of your feasible actions. So in the context of news, your editorial comes with 12 lists of stories, trending stories that should be shown on the page. So 80% of the time, we will show the news that we think you like, and 20% we will randomize over this list of 12 articles and propose a different type of article and see if the user reacts positively to it, and that's our positive reinforcement feedback for this algorithm. It turns out that exploration is so powerful because it allows you to now label your data set automatically. You don't need to go and spend money labeling a data set because every positive reinforcement is a label. And anytime you're exploring, you're actually increasing your data set. So this gives you a very rich data set that you can learn from. And the gold nugget here is to do offline experimentation. So what you see in the black is the actual click-through rate of one of our customers. What you see in the green, in the teal or green, is our estimate offline of that online performance. It's a mouthful, but imagine that you can actually estimate that performance offline, and there are mathematical proofs for this. So this is really founded in mathematics. And then underneath this is what the click-through rates would have been with just the editorial. Now, with this offline experimentation, you don't have to just plot your offline estimate of the actual performance. You can go and run 1,000 A/B tests in a minute, effectively, and plot all of these policies and determine which one is going to work best with you without ever having actually set up an A/B test. This is very good because now all of a sudden you go from performing an A/B test that tests two models to actually collecting the data first using this exploitation method. And then offline, you can run thousands of experiments, right? You're not bound by actually setting up an A/B test, waiting for 2 weeks, analyzing the data, and coming back, and it fails, so you go swizzle it again, and you try it. Now you can run 1,000 of them offline, and once you've found that policy that is going to increase your business outcome, then you can A/B test it. So this custom decision service is this technology that we built. It's something that we're previewing at the moment under cognitive services in Azure. So if you go on Azure Cognitive Services, you'll see this service. We have validated it with a few of our partners. So MSN is Microsoft's search website. We gave them a 26% lift over their editorial. We have a great partner, complex.com. There we personalize video feeds as well as trending stories, and we give them on average a 40% lift over their editorial. We have another partner, Track Revenue. There it's interesting because their business outcome is not clicks, it's actually revenue because they are a marketing campaign partner. So they can map their clicks to their revenue, and we give them 30% revenue. We just started flighting with Xbox. So Xbox is our flagship gaming at Microsoft. And within 2 weeks, we were able, this is for ad campaign targeting. So we're personalizing the ads that the Xbox users see on their console. And within 2 weeks, we gave them, just 2 weeks of running the model, we gave them a 10% lift over their click-through rate. So it's very powerful. And what's really nice about this, it's not just an API, it's an entire system that basically has a prediction and exploration at the front of it. It has an online learner. This is doing near real-time learning. So there's on every single impression, the learning is being done. And there's a way that we log everything under the customer's subscription. So we're, as Field was saying, all GDPR compliant these days, which is kind of nice. And we have, so it's an entire life cycle that goes behind the scene. So let me, Samir, let me end up by just reiterating why use reinforcement learning. Well, the most important thing is that it's cheap, right? Because it uses free interaction data rather than expensive labels. So that's kind of nice. Second, if you are in a field where content is changing underneath your feet, this type of technology works very well for non-stationary data. And third, if you have data scientists that you go and say, you have to increase my click-through rate within 24 hours, and they're scratching their heads, you know, saying, oh my God, how am I going to do this? Then with this type of technology, you can do offline experimentation and make your data scientist life a lot easier, because it's a huge improvement in efficiency when you can run all these A/B tests offline. That's it. Thank you.
I have two questions.
Sure.
First question is, I'm not sure I'm following the offline experimentation. How are you collecting the data if it's offline? And the second question is on the thousands of examples that take the dogs and the cat situation. I may like Dobermans, but I don't like to see them attacking people. Or I mean, if I'm a cat person. Or I may not like Dobermans, but I like Golden Retrievers.
Right.
So how much fine-tuning is there to discover that I'm never going to see a Doberman video, because the Doberman video showed me one of attacking people,
Right.
even though I'm a
Right.
cat person.
So let's talk about the offline experimentation. It's a little bit tricky. So what happens in our system is that every time we give you what the model chooses for you as the most likely that you will like, we gather that data, right? It's okay. I clicked on Dobermans. That's good. I have a click. I have you as a user profile, and I have what you clicked on, the features of the articles. And every time I randomize, so now I'm giving you something very different, I'm actually capturing that data. So what's effectively happening in this system is that I am recording, your behavior.
Even if I'm offline?
No, you have to be interacting with the system. And, but this is across, you know, we're pooling on user profiles. So it's not Rafah specifically, it's my feature set, like people that resemble me, basically. And what I have is a set of data and the probability that I will click on Doberman versus Havanese versus whatever. And then offline, what I'm doing is I'm asking the system, how would have this model behaved with this set of users? So that's the kind of question I'm asking of my system, versus, is my model A better than my model B, which is what you do in A/B testing. So it's an inverted way of looking at the A/B testing in some sense. And that's why you can run these things offline, and you can ask them 1,000 times over and over again.
So the offline is at your end, not at my end?
No, I mean, we offer the tools for your data scientists to do it.
No, what I'm saying is that I'm no longer online,
You're no longer online, that's right. The learning is happening online, but the offline experimentation is happening offline, right. Okay, now going back to the second question, this model is only as good as the features that the data scientist, our end customer, chooses to report on. So as the richer the context, the more fine-grained that learning could be.
Define the Doberman content as
versus
Doberman content or
exactly.
Doberman attacking people,
exactly.
Doberman puppies.
Exactly. So we work with the data scientists with our end customer and say, hey, like what features do you have that you can expose to us? And the richer, the better the learning is. Any other question?
I have actually like two, but they're connected. First, let's say I don't have any data. Like, what's the critical mass of those events in the past?
Yes.
If they only apply to
Yes.
yes. Right? And the second, related to the first one, at what point you decided that the system is ready for the offline experimentation, that it's knowledgeable enough to give you like predictive results rather than randomly picking?
Yes, they are related. So actually, it's a little bit complicated because it depends on how many impressions you as a customer get on your whatever website or device. So the more events you get, the sooner you can do offline experimentation and the quicker the learning is. So the number of impression is important as well as the features. So, and the number of actions. So all of these three things are interrelated. So the more events you have and the smaller the number of action space that you're trying to optimize for, the quicker the learning. If you had 50, if you say, okay, I have a recommendation engine, suppose, and you have a playlist, right? And I'm going to recommend 50, and you want to use our system to personalize amongst the 50. That can happen faster if you have 10 million events per day versus 1 million event, right? Because you have a richer data that the online learner is seeing. And the same goes for offline experimentation. So in Xbox, for example, we showed them an improvement after 7 days. We were up 5% because they get, in the order of 13 million a day events. So it's pretty rich.
Well, yeah, I kind of get the point about the events, the more the better. Like
and the feature set.
Like the actions should be less number of actions. So like it's like
yes, because remember.
Dogs, like, dislike.
So
like if you give these options to the system, you get better results rather than giving them a choice of 3, for example.
yeah, because remember that this is a system that is doing both prediction and exploration. If your space on which you're exploring is very big, you're going to take a longer time to learn. Whereas if your exploration space is small, then you can learn a lot quicker. Any other questions? Okay, well, coffee break. Thank you all.